Hello and welcome. This is the second lecture on light. This is lecture L in the Natural Science 102 course here at DCC in spring of 2022. And we've talked about how light will bend as it enters. If it goes from air to glass, for example, or air to water, you're going from a less dense medium to a more dense medium, and the light will bend towards the normal. We talked about the angles there. And then we talked about the situation where light passes from, like, say, water to air or glass to air. In other words, from a more dense medium to a less dense medium. And we said that light would bend away from the normal. And we talked about the angles there. Now, the applications for this are in the use of lenses, okay? Rainbows that you see in the sky are as a result of light bending as it passes through a water droplet, and your vision is possible because light passes through the lens of the eye to converge light and focus it onto the back of your eyeball and produce an image. And eyeglasses, for example, are glass that corrects deficiencies in the lens of your eye to bend light in certain ways so that your image will be nice and clear as you wear your safety glasses. These are the two main types of the ray diagrams for the couple types of lenses I want to talk about, okay? Up here in the top, we have a convergent lens. This is called a convergent lens because light rays that strike the lens in a parallel fashion like this are all bent and focused to a single point. They cross eventually, but the focal point is right where all of these light rays intersect, okay? So that right there is the focal point. And so this is a convergent lens because all of the light is coming together or converging at a single point, okay? So that might be found in a magnifying glass, for example. Sometimes you can go out into the field, right, and hold your magnifier glass in front of the sun, and then carefully raise it or lower it to the ground so that you get a pinpoint of light hitting a single spot, and you might be able to catch a blade of grass on fire or a paper on fire, okay? So that's an application of convergent lenses, okay? So all of the light rays are focused to a single spot, and that's what the word focused means. It means, one spot, basically. I'm going to say a single point. It's really a three-dimensional situation, like with a lens, magnifying lens. All right, down here we have something called a divergent lens. A divergent lens is opposite, okay? So parallel light rays are coming in from the left. And what happens is that the rays of light diverge or spread apart, okay? So it's completely different. And there's no, in this case, for my class, I'm going to say that there's no focus, okay? In the strictest sense. There is an imaginary focus, or it gets weird, but we're not going to talk about any of the mathematics of calculating any of these things. Now, so let's write down what we have. Light rays are spread apart or dispersed. So this has certain applications in photography and other kinds of compound lenses, but this would not make a good magnifier glass because the light's spreading apart. So where would you actually see these lenses? Well, let me show you something here. I'm not sure if you can see this image right here. This is the iPhone 13 Pro, and on the back of the phone you have different cameras, a wide angle, a macro lens, and different things, okay? So depending on how close you are to a subject or how far away, the camera will automatically detect the better lens to use to take that photo, and it's very complicated. The phones and the optics and the camera processing within cell phones is very advanced nowadays. It's not quite as good as a DSLR digital camera, of course, but the cost of these things are equal to or greater than, a Canon or a Nikon camera. Now, within this camera element, you can see these little discs here of different shaped, they look like glass. They're kind of reflecting the light there, so you can kind of see that they look like they're glass or plastic or acrylic maybe in this photo here. And there's a whole bunch of them, okay? So those lens elements are all in there to design the exact way that the light is focused and projected onto the sensors so that you get a good picture. And some of these might be diverging lenses, some of them might be converging lenses. And you might wonder, well, why are there so many lenses in there? Optics design is a very complicated business, but especially with cell phones, you're limited with a camera that might be only a few millimeters thick. Okay, the lens here can't extend like a telephoto lens, or it can't be like a Nikon camera that's really thick and big. Okay, you're limited to a certain thinness, okay? So each one of these might be very thin, not as thin as a piece of paper, but less than a millimeter or maybe a millimeter in thickness, and they're all jammed in there, okay? And in fact, if you look at the cell phone cases, the camera actually protrudes outside of the phone case. It's no longer flat, okay? The older originals, iPhones up through iPhone 10 or and before, were flat, completely flat on the back, but now the lenses are a little bit bigger, okay? They're getting bigger. So they're trying to get this as small as possible, and that's why you have so many lenses in series, okay? Now I want to talk about light as a wave. Light is called electromagnetic radiation. And you can see electric, and then you can see magnetic in there, okay? Now, there's an oscillating electric field and there's an oscillating magnetic field, but I'm just gonna draw a simple wave here on the board just to highly simplify things, okay? This is a very basic science class, and it's not meant to go into the frequency, the wavelength, and we're not gonna talk about the speed of light in this section of the class. So, here's a wave, okay? And I'll just put an arrow over here, and you can think about like if I pulse a laser, if I hit the button on a laser pointer, I turn it on and then I turn it off for a moment. So there's a certain wavelength of light that's passing through the air, and a certain frequency of light that's passing through the air as it goes from one point to another. So that kind of represents the wave. Now, sunlight, when it comes in through the Earth's atmosphere, okay, when it's emitted from the sun, let's say, the wavelength could be going like this. Okay, now I know this is sideways, okay, but I'm pretending like my head is the sun and the camera is you as the observer, and the light could be oscillating like this as it comes from the sun to you, okay? And look at my hand. It seems to be going up and down. So that is a direction of the wave as it's coming to you, okay? And we call that its orientation. So it might be vertical, okay? What if the wavelength of light snakes like this, like a snake, and it's coming towards you like this? If you look at my hand, it looks like it's going left and right, left and right. So that right there is a direction of the oscillating, you know, say electric field or the magnetic field, okay? It's going left and right, okay? So these arrows with the two heads, one's pointing up, one's pointing down, just means the direction of the oscillation, okay? And this one horizontally is the direction of the oscillation as a wave makes its way towards you. I wish I had a slinky and I could do this somehow with the video, but I don't have a slinky also. Okay, so this is a vertical and this is a horizontal orientation of the light rays, okay? Now, when you have many of them coming from a source, you have all of these possibilities, okay? So the sunlight that comes from the sun could have waves that are going like this, waves that are going like this, waves that are going, you know, at all different kinds of angles and stuff. And so this is a typical diagram that shows unpolarized light. We have oscillations or orientations in all possible directions. It's not a good sentence there that I phrased, but the orientations and oscillations are in all possible orientations or oscillations, okay? So one part of the light might be going like this, another part of the light might be going like this, another part of the light might be going like this, and all those combined are indicated with this diagram. Okay, notice the use of the double arrows to show how they're orientated in all different possible orientations. Now this here is polarized light. And we'll talk about different ways that we see this situation occurring, but pretend like you had some kind of filter or some way to make all the light always going vertical, okay? So one light is this way, another part of the light is this way, and they're all, you know, many different beams of light that are coming from the sun, for example, are all oscillating in the vertical fashion only. You don't have any in the horizontal or any other angles, just the up and the down. So that's vertically polarized light, okay? So this represents polarized light because you only have one of the oscillations, okay? Now, we have these things called polarizers, okay? A polarizer is a lens, a filter, a device, some object like water, for example, or there's atmosphere that causes light in many different oscillations or orientations to become polarized, and polarized light has only one oscillation. It could be horizontal, it could be vertical, it could be any other arbitrary angle, okay? So this grid here, this rectangle, not sure if you can see this too well on the camera, but this grid here, it's just a polarizer, okay? It's a we say it's a filter, okay, and it's a polarizer, okay? So a polarizer, okay, filter that allows only certain orientations of light to come through. Okay, so let's take a look at what we have over here. Again, I'm not sure if you can see too well on the camera, but we have unpolarized light here in this top figure, okay? Light is present vertical, this angle, so it's many different orientations of light, and it hits this filtering element, okay? It actually has two of them. I don't know why it has two in this diagram, but as it passes through that, okay, it only allows the vertical orientations to pass through, okay? And so what we have afterwards is vertically polarized light, okay? So we can see how all of the arrows are just pointing up and down, okay? Down here, we have two polarizers. It's very interesting, okay? We have unpolarized light that's coming through at many different orientations. And our first polarizer is going to block out and only allow vertically polarized light to pass through, okay? And that's what you see right here. But then the next polarizer only allows light that's in the horizontal orientation to pass through. Because the light is vertically polarized at the middle point, at this point, okay? When you put the polarizer next, that only allows horizontally polarized light to pass through, no light passes through, okay? So this will block both types of light. So if you have a polarizer that allows only vertical polarization to go through, followed by a polarizer that only allows horizontal light to pass through, we call that a cross-polarized setup, and it blocks all light, okay? So it would be completely black. So cross-polarizers. These are going to block all light. It contains two polarizers. The first polarizer it allows only the vertically polarized light to go through. So that's why you do have vertically polarized light in the middle, and then the next polarizer blocks everything. It allows horizontal light to pass, but since it's already been blocked, there is no light that's horizontal. So I'm just going to say it's black. Okay, so if this was a bright white light in the middle, it'd be dimmer because you're only allowing some light to pass through. And then at the end, you have no light. So that's what that label right here says on the slide. It says no light. And I know here in the text, I say it's black, but black for me just means no light. It's dark, very dark, okay? So where do you see these kinds of devices? Let's look at, first of all, what types of things can polarize light? So the Earth's atmosphere, for example, can polarize light. Here we have a puddle, okay? So we have a puddle, and the sunlight here is releasing unpolarized light. And you can see how the arrows are going in all different directions. And when it interacts at a small angle and reflects off of light, off of the puddle of water, we have horizontally polarized light. Horizontally polarized light. Okay? So let me show you where we can use this information. So here's a pair of sunglasses. Back in the day, they used to call these Polaroids. Polaroid sunglasses are still made by Polaroid. And these are designed to filter out horizontally orientated light. So remember that bicyclist who was looking at the puddle and seeing all the horizontal light coming? These glasses are designed to block horizontally polarized light so that this biker wouldn't be affected by glares off of windshields, puddles, things like that. But of course they would see sunlight hitting everywhere else because it's not being polarized as it hits normal rocks and things like that. Okay. So one of the things you can do, I have clip-on lenses for these glasses. I think I left them in my office. But one of the things you can do is if you're buying sunglasses and you want to know if they're polarized, take off the sunglasses. Don't look right into the sun, okay? Just look at, a blue part of the sky. And hold your sunglasses like this, okay? And then look through the lens and then orientate it vertically, okay? So hold your glasses like this, look through, and then hold your glasses like this and look through, and you should see a difference in the color of the sky, okay? And if you see that difference in the color of the sky, you know that you have polarizing lenses or polarized sunglasses, and those are a good type of sunglasses. They're just not shaded kind of shades. The sunglasses can be called shades, but these would be polarized sunglasses, which are very good. They tend to be more expensive, okay? This is what I'm talking about here. Let me see if I could zoom in a little bit with this. I think I might need the mouse, hold on. All right, this is from Wikipedia. You can look at these articles yourself. So right here is a photograph of the sky without using any polarizer at all, okay? You can see how there's not much contrast. The sky looks kind of like almost white, maybe a pale blue. And then over here on the right is the same photograph, same scene, but somebody's attached a polarizing lens onto their camera. And you can see how it's much deeper blue. You have great contrast with the clouds. You can see stuff, okay? It's just the contrast is so much greater, okay? So that's what you want to do if you're buying sunglasses at the beach or at the eye doctor or whatever. Are these really polarized? Walk over to the window and hold them up like this, like you would normally wear them. The sky should look like on the right. Turn it 90 degrees. The sky should look like that, okay? That's a nice little test you can do to test that you're getting your money's worth. Remember the bicyclist that was seeing that polarized light reflected off of that puddle? I've seen really amazing pictures of an alligator, partially submerged in the water. And then there's an unpolarized picture where you just see like water glare. And then there's an unpolarized picture where you can see right into the water and it's crystal clear. Here we're taking a photo of the beach, okay? On the left, you can see these are waves here. This white feature here is a wave coming in. And you can see how it's very shiny and reflective. And on the right, it's much less shiny and reflective. Here's some trees. We can see how there's reflection off of these leaves, and they're very shiny, okay? And then over here, this is the polarized light. Now we can see how we can actually see things, okay? The leaves. Here's what I was talking to you about. If you have a lake or something and you're taking a picture, you're seeing a whole bunch of reflection off the surface of the water. It's very white. And then you take a picture over here, you can't even see the water. You're just seeing rocks on the bottom of this lake or stream. And so you don't even see the water. It's almost like, wait, where'd the water go? Well, it's still there. It's just not reflecting that polarized light because you've blocked it with the polarizer. And then there's other things in there I don't really want to talk about, okay? So that's an application of polarized light using sunglasses to block that unwanted glare from windshields, signs, and whatnot, especially in the morning hours or the evening hours when the sun is low to the horizon, okay? Because you're going to be looking kind of right at it, and it's going to be giving a lot of reflection into your eyeballs. But at noon, it's not so much of a problem because the sunlight is passing directly down on you, okay? So that's maybe when you would need shades or, just the blocking feature to prevent ultraviolet light from hitting your eyes and causing damage, okay? I believe that's all I wanted to talk about for this chapter. So in summary, we've learned a little bit about light, how it interacts and bends. We call that refraction. And when light reflects off something like a puddle of water, we call that reflection. And we now know that the Earth's atmosphere and puddles can polarize light. When light bounces off of those objects or leaves or a person's windshield, it will polarize the light in a horizontal fashion. So if you have a good pair of polarizing sunglasses, you can look right into a glare and you won't see the glare, okay? You'll just see the normal kind of sunlit scenery. We've talked about light, how it's a wave, and we've talked about converging and diverging lenses, which piggybacks on the first lecture where I talked about how light bends away from the normal or towards the normal, depending on what kind of medium it's traveling from and to. Okay, so that's it, short class today, but I hope you know a lot more about light and lenses and your camera and have an appreciation for technology. Thanks for watching. Please like and subscribe. Have a great day.